I'd like to take a look at a couple of problems that take our equations about light and just turn them to a higher level. And so by that, I mean story problems that require us to pull information out and transform it in some way. So here's our first one. Our first one involves looking at oxygen in the, or ozone, sorry, O3 in the stratosphere. And in particular, oops. I'd like to take a look at some of these more fiddly story problems that involve working with information and light equations like we've had in this most recent chapter. The equations themselves, right, we know those are simple. Things like E equals h nu and C equals lambda nu. And then, of course, by algebra, E equals hc over lambda. Those are not difficult. But pulling the information out to do something with it in a problem can be. And so here I see information, and this is one of our challenge problems, about the kilojoules of energy to break 1 mole of O3, ozone bonds. And I see 3 goals, right? Our goals are energy of the photon, so energy of 1 photon. Right, so there's goal number 1. And I see goal number 2 is the frequency. And again, that's going back to 1 photon, so frequency. And then the third one is the wavelength. So I know that by the time I get done, I'm going to find E and nu and lambda. And I also know that I'm starting with information that relates the amount, so 445 kilojoules of energy per 1 mole O3. Well, 1 photon and 1 mole of photons are not the same, so let's do a quick conversion here. All right, I know that there's 1 kilojoule has 1,000 joules, and I know that 1 mole has 6.02 times 10 to the 23rd in it. When I do that math, you notice that moles have canceled, kilojoules have canceled, and then this is a single photon, so I'm left in joules. And so it's 7.39 times 10 to the negative 19 joules in 1 photon. All right, I've divided out the fact that there were a lot of photons in this original. Now, I might as well just take that information and go on, right? I know the energy, and I know that energy and frequency are related. I know that I have E equals h nu. I just found the energy. I know Planck's constant because I looked it up. And I'm solving for nu. And so I'll divide both sides by Planck's constant. And I'll find that nu is equal to 1.16 times 10 to the positive 15 hertz. So there is my frequency. Last but not least, energy. I know that C is equal to lambda, and I know my nu now, 1.16 times 10 to the 15 hertz. So lambda must be 2.69 times 10 to the negative 7, and I know that that comes out in meters, right? What did we ask for? We asked for nanometers. Make sure you go back and check that problem. What do I know? I know that 1 meter has 10 to the 9 nanometers in it. So this ends up being 269 nanometers. By the way, that's the ultraviolet range, and that's why UV light from the sun, if it goes to the ozone layer, gets destroyed because the ozone takes it out. But without the ozone layer, that comes down to us and causes problems. So this is one fiddly story problem, right? Find the information, figure out where it goes in the equations. Let's take a look at another story problem. This one, it looks like we are being asked to get the total energy and the total number of photons in one laser pulse, right? So goals, energy of a laser pulse, and photons in one laser pulse. And the only information we have is the wavelength of the laser and the pulse length, so how long the laser is pulsing. Let's think about energy first, because that 1.06 microns can get us to a place, right? We know that energy is equal to hc over lambda, right? I'm putting my energy together with my wavelength equation. I know Planck's constant. And I know the speed of light. And I know the wavelength as well. It's actually 1.06 times 10 to the negative 6 meters. That conversion is one that I know and I used here, but you would be given a conversion like that on a test. So let's see. We have 6.626 times 10 to the negative 34 times 2.998 times 10 to the 8 divided by 1.06 e negative 6. 1.87 times 10 to the negative 19 joules. Let's take a look at a different, Let's take a look at a different type of story problem that has a little bit of outside information built into it. So we've got a problem that appears to be asking us to find out the number of photons that are in a laser pulse. And the information that we have is the wavelength of the laser and the pulse energy. So how much energy is in a whole pulse. And what I want to call your attention to, let's kind of divide this in half, right? We've got one photon, and we've got all the photons in the pulse. And that 1.6 or 1.06 microns, by the way, that's 1.06 times 10 to the negative 6 meters, right? That's a property of a single photon. One photon has that wavelength, and so does another one, and so does another one. It's a property of individual photons. Whereas together, right, the total energy is equal to 1 millijoule, or remember that there's 1,000 millijoules in a joule, so it's 0.001 joules total. That's all the photons together. Well, we have an equation, don't we? We know that E equals hc over lambda applies to one photon. So let's solve it. All right, so E equals Planck's constant times speed of light over 1.06 times 10 to the negative 6. So the energy of a single photon is 1.87 times 10 to the negative 19 joules. Okay, so let's set up a proportion. We know that 1.87 times 10 to the negative 19 joules represents the energy of one photon. And we know that 0.001 joules represents the energy of all the photons. So we'll call it X. So let's cross multiply and solve. 1.87 times 10 to the negative 19 times X equals 0.001 joules. And then X equals 5.35 times 10 to the 15 photons. By the way, that's far less than a mole, so it's actually a pretty small number as far as a collection of little bitty things goes. But this whole problem rests on the fact that all of these light equations apply to individual things, and sometimes you're given collective properties and you have to put those together via proportion. So don't forget about your power of being able to do proportions and make those matches going forward, and that'll help you with some of these story problems. Good luck!